Hello, and welcome to the 67 Sleepy Facts channel. Before we begin, know that this video is like a double-edged sword, which will either help you sleep or might keep you awake. Either way, it's better than doom scrolling at 2 a.m. If this feels like your corner of the internet, then consider a like and subscribe. Now let's begin. You are surrounded by something unimaginably old. Right now, as you read these words, you are immersed in light that has been traveling for more than 13 billion years, photons that began their journey when the universe was only about 400,000 years old, when space itself first became transparent. This ancient radiation fills every cubic centimeter of existence. You cannot see it, but instruments can. It passes through walls, through your body, through the space between your atoms, carrying with it a faint, persistent whisper from the birth of everything. Scientists call it the cosmic microwave background. The cooled afterglow of the Big Bang stretched and diluted as the universe expanded, now lingering as faint microwave radiation. There is nowhere you can go to escape it. You are constantly moving through the echo of creation itself, usually without ever knowing it. But hidden within this ancient light is something deeply unsettling. It is not perfectly uniform. It contains tiny temperature variations, regions microscopically warmer or cooler than their surroundings. These fluctuations are the seeds from which all galaxies formed, the amplified imprint of quantum fluctuations from the universe's earliest moments. By studying these patterns, astronomers can predict how much matter the universe should contain today and how it should be distributed across the cosmos. And when those predictions are compared to what we actually observe, the numbers do not come close to matching. There is nowhere near enough matter. All the stars, galaxies, gas, and nebulae we can see with our most powerful telescopes account for less than 5% of what the universe's own earliest light says should exist. The rest does not shine, does not reflect, and does not reveal itself in any familiar way. And yet, without it, the universe as we know it could never have formed at all. Something invisible dominates our universe, and we have no idea what it is. 70% of everything that exists is made of a force so strange that the world's most brilliant physicists can only give it a name that confesses their ignorance: dark energy. Not dark because of its color, but dark because it represents the deepest mystery in all of science. It's the cosmic equivalent of realizing that most of the house you live in consists of rooms you've never seen, doors you cannot open, and hallways that stretch into dimensions you cannot comprehend. Every night as you drift towards sleep, this mysterious force is pulling the universe apart, stretching space itself, accelerating everything away from everything else in a cosmic expansion that defies every intuitive understanding of how reality should behave. The remaining 25% consists of dark matter, another invisible substance that reveals itself only through gravitational effects. Galaxies rotate too fast. The stars on their outer edges should be flung into space by centrifugal force, but they aren't. Something unseen is holding them together, providing additional gravity that cannot be accounted for by visible matter. Galaxy clusters behave similarly, containing far more gravitational mass than their visible stars can explain. When astronomers observe gravitational lensing, the bending of light around massive objects, they find that space is being warped by matter they cannot see. Invisible scaffolding pervades the universe, a cosmic skeleton that holds everything together. Scientists have searched desperately for dark matter particles, building detectors deep underground to shield them from cosmic ray interference. These experiments wait in silence for a dark matter particle to collide with an atomic nucleus, an event that might happen once in years of observation. Thousands of kilograms of ultra-pure materials sit in caverns kilometers below Earth's surface, waiting for a signal that would revolutionize physics. So far, they've found nothing. Whatever dark matter is, it interacts so weakly with normal matter that it passes through entire planets without leaving a trace. Trillions of dark matter particles are streaming through your body right now, and you will never feel them.
The discovery that shattered our understanding of the universe came from watching stars die. Supernovae, those spectacular final acts of massive stars, explode with such consistent brightness that astronomers can use them as cosmic measuring sticks. When a white dwarf star in a binary system accumulates too much mass from its companion, it reaches a critical threshold and detonates in a Type 1a supernova. Because this threshold is always the same, these explosions always reach approximately the same peak brightness, making them standard candles visible across billions of light years. By comparing how bright these stellar death throes appear versus how bright they should be, scientists can calculate their distance with remarkable precision. It's the same principle as watching car taillights recede into the distance, judging how far away the vehicle is by how faint the lights appear. But when Saul Perlmutter and his team measured distant supernovae in the late 1990s, they discovered something that shouldn't have been possible. The universe wasn't just expanding, it was accelerating, speeding up, getting faster with each passing moment. The distant supernovae appeared fainter than expected, meaning they were farther away than they should be if the universe were expanding at a constant rate. Space itself was stretching faster now than it did in the past, as if some invisible force was pressing down on the cosmic accelerator, pushing everything apart with increasing vigor. This revelation hit the scientific community like a psychological earthquake. For decades, cosmologists had assumed the universe's expansion would gradually slow down, like a ball thrown upward, eventually succumbing to gravity's pull. The energy from the Big Bang should have been running out, they thought, causing the expansion to decelerate over cosmic time. Einstein himself had introduced the cosmological constant into his equations as a fudge factor to keep the universe static, then later called it his greatest blunder when Edwin Hubble discovered the universe was expanding. Now it seemed Einstein's blunder might have been prescient. The cosmological constant, reinterpreted as dark energy, could explain the accelerating expansion. Instead, Perlmutter's observations showed the exact opposite. Something was pushing everything apart with increasing vigor. Astronomers walked around in a daze, scratching their heads, insisting the data must be wrong. Surely this couldn't be right. But repeated observations confirmed the impossible. The universe was accelerating, driven by some unknown force that permeates all of space. Independent teams reached the same conclusion. The evidence became overwhelming. In 2011, Perlmutter shared the Nobel Prize for this discovery that upended cosmology. What makes dark energy so profoundly unsettling is that it seems to violate basic principles of physics. As the universe expands and space stretches, you'd expect any energy filling that space to become more diluted, spread thinner across a larger volume. But dark energy doesn't behave this way. As space expands, dark energy remains at constant density. You get more space, and somehow you get more dark energy with it. It's like filling a balloon with air and discovering that the air inside somehow multiplies as the balloon inflates. Something for nothing. A cosmic free lunch that breaks the rules we thought governed reality. The universe is creating energy from nowhere, or at least from somewhere we cannot detect or understand. The implications become even stranger when you calculate the energy density of the vacuum. Quantum field theory predicts that empty space isn't actually empty, but seethes with virtual particles constantly appearing and disappearing. These quantum fluctuations should contribute energy to the vacuum, and when physicists calculate how much, they get a number that's catastrophically wrong. The predicted vacuum energy is 10 to the power of 120 times larger than what we observe. This is the worst prediction in the history of science, off by a factor so enormous it suggests something fundamental is broken in our understanding of reality. Either quantum field theory is wrong, or general relativity is wrong, or both are wrong in ways we cannot yet comprehend. Scientists have proposed various explanations for what dark energy might actually be, and each possibility sounds more bizarre than the last. Perhaps it's a new type of field permeating all of space, similar to electromagnetic fields but operating on cosmic scales. This hypothetical field, called quintessence, might vary in strength over time and space, changing as the universe evolves. Maybe it's a new particle, something as fundamental to reality as electrons or quarks, but existing in a form we haven't yet detected. Some physicists suggest it could be a property of space itself, a background energy inherent to the vacuum of empty space, the cosmological constant Einstein stumbled upon.
There's even speculation about chameleon particles, hypothetical entities that change their mass depending on their environment. In regions of high density like Earth's surface, these particles would be heavy and difficult to detect. In the vacuum of space, they would be light and could drive cosmic acceleration. Experiments at Berkeley attempt to detect these elusive particles by watching cesium atoms fall in a vacuum, searching for subtle deviations from expected gravitational behavior that might reveal this hidden force. The atoms are suspended above metal spheres, free to fall subject only to Earth's gravity and the potential chameleon force. So far, no chameleons have revealed themselves, but the search continues. Another radical possibility suggests that our understanding of gravity itself is incomplete. Perhaps general relativity, Einstein's masterwork that has passed every test for over a century, breaks down at cosmic scales. Modified gravity theories propose that gravitational attraction behaves differently over distances of millions or billions of light years. These theories can sometimes explain cosmic acceleration without invoking dark energy, but they struggle to match all observations. Most physicists remain skeptical, preferring to believe in mysterious new forms of energy rather than abandoning Einstein's elegant framework. The search for dark energy has driven the construction of increasingly powerful telescopes pointed at the deepest reaches of space. The Dark Energy Spectroscopic Instrument, DESI, maps millions of galaxies across cosmic time, measuring how their distances have changed as the universe evolved. Mounted on a telescope in Arizona, DESI can observe 5,000 galaxies simultaneously, building a three-dimensional map of the universe that extends billions of light years in every direction. The further away a galaxy appears, the younger it is, because light takes time to travel across the cosmos. When we observe a galaxy a billion light years away, we're seeing it as it existed a billion years ago, when the light we're now receiving first began its journey. By mapping galaxies at different distances, astronomers can trace the expansion history of the universe, watching how dark energy's influence has changed over billions of years.
They can measure whether dark energy has remained constant or varied over time, whether it's strengthening or weakening, whether it will continue driving acceleration forever or eventually reverse. Each data point constrains theoretical models, eliminating possibilities that don't match observations. The work is painstaking, requiring observations of millions of galaxies to achieve the statistical precision needed to detect subtle differences between competing theories. The European Space Agency's Euclid telescope represents humanity's most ambitious attempt yet to solve this cosmic puzzle. Launched into orbit at a gravitationally stable point between Earth and the Sun, this spacecraft dwarfs even the iconic Hubble Space Telescope, capturing images of 625 megapixels every 10 minutes. That's roughly 300 high-definition television screens worth of data flooding down from orbit twice an hour. In a single day, Euclid collects as much information as Hubble gathered in its entire multi-decade lifetime. This torrent of cosmic data might finally narrow down what dark energy actually is, eliminating hundreds of theoretical models that can't match observations. Euclid employs two primary methods to study dark energy. First, it measures weak gravitational lensing, the subtle distortion of galaxy shapes caused by intervening dark matter. By analyzing how billions of distant galaxies appear stretched and warped, scientists can map the distribution of dark matter across the universe and watch how it has evolved over time. Second, Euclid measures baryon acoustic oscillations, cosmic sound waves frozen into the large-scale distribution of galaxies. These features, imprinted when the universe was just 380,000 years old, provide a standard ruler for measuring cosmic distances. Together, these techniques allow unprecedented precision in tracking the universe's expansion history. Scientists hope that within this ocean of information lies the key to understanding the force that dominates our universe. Euclid will observe a third of the sky over 6 years, cataloging billions of galaxies and measuring the positions of tens of millions with extreme precision. Pattern recognition algorithms sift through the data, looking for subtle statistical signatures that human eyes could never detect. The telescope might reveal that dark energy is changing over time, strengthening or weakening in ways that would fundamentally alter predictions about the universe's fate. Or it might show that dark energy is precisely constant, matching Einstein's cosmological constant perfectly, a result that would be scientifically satisfying but philosophically unsettling. But dark energy is only part of the cosmic mystery. Another 25% of the universe consists of dark matter, an entirely different unknown substance that reveals itself only through gravitational effects. Together, dark energy and dark matter make up 95% of everything that exists. The stars, planets, galaxies, and all the matter we can see and touch constitute a mere 5% of cosmic reality. We are essentially living in a universe composed almost entirely of things we cannot see, cannot touch, and cannot explain. It's as if we're trying to understand a vast ocean while only being able to perceive the foam on the waves, completely blind to the dark waters beneath. Computer simulations of galaxy formation reveal just how crucial dark matter is to cosmic structure. When scientists model the universe using only visible matter and known physics, galaxies don't form properly. Stars and gas clouds don't have enough gravity to clump together into spiral and elliptical galaxies we observe. But add dark matter to the simulation and everything works.
Dark matter forms vast halos surrounding galaxies, providing the gravitational scaffolding that allows normal matter to collect and form stars. These dark matter halos extend far beyond the visible edges of galaxies, creating invisible cocoons that contain most of a galaxy's mass. The nature of dark matter remains one of physics's greatest mysteries. The leading candidate is a hypothetical particle called a WIMP, a weakly interacting massive particle that would have been created in abundance during the Big Bang. WIMPs would have cooled and clumped together through gravity, forming the cosmic web of dark matter that normal matter fell into. But decades of searching have found no evidence for WIMPs. Detectors buried in abandoned mines and deep underground laboratories have seen nothing definitive. Some physicists are beginning to doubt whether WIMPs exist at all. Alternative dark matter candidates include axions, hypothetical particles billions of times lighter than electrons that would exist in enormous quantities. Sterile neutrinos, particles that interact even more weakly than regular neutrinos, might also contribute to dark matter. Some theories propose primordial black holes, tiny black holes formed in the universe's first moments that could account for some or all of dark matter. Each possibility requires different detection methods and makes different predictions about dark matter's fundamental nature. The diversity of proposals reflects deep uncertainty about dark matter's fundamental nature.
The implications of dark energy extend far beyond abstract physics into the ultimate fate of our universe. If this accelerating expansion continues, it will eventually tear apart the cosmic structures we see today. Galaxies beyond our local cluster will accelerate away from us faster than light can travel, disappearing beyond an ever-shrinking cosmic horizon. In the far future, astronomers in distant galaxies might look at empty skies, unable to see any other galaxies at all, completely isolated in an expanding void. The Milky Way and its nearest neighbors will become island universes, cut off from the rest of creation by expansion that has carried everything else beyond the observable limit. This future is already beginning. The Virgo supercluster, a massive collection of thousands of galaxies that our Milky Way orbits at a distance of about 65 million light-years, is slowly slipping away from us. The space between us and Virgo is accelerating faster than gravity can pull us together. Eventually, Virgo will accelerate beyond our cosmic horizon, becoming forever unreachable. Future civilizations in the Milky Way, should they arise, will never be able to visit or even observe these galaxies. They will have disappeared as completely as if they never existed. Even more disturbing scenarios emerge from certain dark energy models. If dark energy's strength increases over time rather than remaining constant, it could lead to a big rip where the accelerating expansion eventually tears apart galaxies, then solar systems, then planets, then molecules, then atoms themselves. Calculations suggest this could occur approximately 22 billion years from now if dark energy follows specific mathematical forms. The universe would end not in fire or ice, but in complete disintegration, with space expanding so rapidly that even the fundamental forces holding matter together cannot resist. The Big Rip scenario proceeds in terrifying stages. First, about 60 million years before the end, galaxy clusters would dissolve as expansion overwhelms gravity holding them together. Galaxies would drift apart, never to interact again. Then, about 3 months before the end, individual galaxies would shred apart, their spiral arms unwinding as stars are flung into the expanding void.
About 30 minutes before the end, solar systems would come unbound, with planets spiraling away from their suns. The Earth would freeze instantly, its atmosphere escaping into space. In the final seconds, planets would fragment, then molecules would dissociate, then atoms would be ripped apart, and finally, in the last fraction of a second, even atomic nuclei would be torn asunder. Space would be expanding so rapidly that forces simply couldn't propagate fast enough to hold anything together. Alternatively, dark energy might change in other ways. Some models suggest it could eventually reverse, transforming from a repulsive force pushing everything apart into an attractive force pulling everything together. This would halt the universe's expansion and reverse it, causing all of space to contract in a big crunch, the opposite of the Big Bang. All matter and energy would eventually collapse back into an infinitely dense point, perhaps triggering another Big Bang and restarting the cosmic cycle. We might live in an oscillating universe that expands and contracts eternally, with dark energy alternating between pushing and pulling across timescales of trillions of years. In oscillating universe models, time becomes cyclical rather than linear. Our current universe might be one of infinite cycles, with previous universes expanding, reaching maximum size, then contracting back to singularities that explode again in new Big Bangs. Each cycle might have different physical constants, different particle masses, different strengths for fundamental forces. Most cycles might be sterile, incapable of forming complex structures. We exist in a rare cycle where conditions permit galaxies, stars, planets, and life. When this cycle ends in a big crunch, all information about our existence would be erased, compressed back into a singularity, and possibly recycled into a new universe with no memory of what came before. The strongest magnetic object ever discovered lurks in deep space, and it has properties so extreme they seem to mock the laws of physics. GROJ 1008-57 is a neutron star with a magnetic field over 1 trillion times stronger than Earth's. This isn't just impressive, it's reality warping. If you approached within 1,000 kilometers of this stellar remnant, your body would simply dissolve. Your atoms would stretch and deform beyond recognition. The molecular bonds holding you together would snap. The electromagnetic forces that give atoms their shape would be overwhelmed by the star's magnetic field. You wouldn't explode or burn, you'd just stop being you. Your constituent atoms warped into unrecognizable configurations before dispersing into space. The magnetic field would affect your body at the quantum level. Atoms are mostly empty space with electrons orbiting nuclei at specific energy levels determined by quantum mechanics. But in magnetic fields approaching 1 billion Tesla, these energy levels shift dramatically. Electrons occupy completely different orbitals. Atoms become elongated, stretched into cigar shapes aligned with the magnetic field lines. The chemistry of life depends on specific atomic configurations and molecular geometries. Change those configurations and biochemistry becomes impossible. Your neurons would cease functioning, your DNA would unravel, your proteins would denature. You would die not from injury, but from having your atomic structure fundamentally rewritten. Neutron stars are created in the violent deaths of massive stars. When a star many times more massive than our Sun exhausts its nuclear fuel, its core collapses catastrophically while its outer layers explode in a supernova.
For a brief moment, the core's density becomes so extreme that electrons are forced to merge with protons, creating neutrons and releasing a flood of neutrinos. What remains is a sphere of matter so dense that atoms cannot exist in their normal form. Electrons and protons are crushed together into neutrons, creating a ball of subatomic particles packed so tightly that a sugar cube of neutron star material would weigh as much as a mountain. A matchbox full would weigh 3 billion tons. The entire mass of a star larger than our sun compressed into a sphere just 20 kilometers across. The formation process is extraordinarily violent. When the star's core collapses, it shrinks from thousands of kilometers in diameter to just 20 kilometers in about 1 second. The core's rotation speed increases dramatically through conservation of angular momentum, the same principle that makes figure skaters spin faster when they pull their arms in. A star that rotated once every 30 days might end up rotating 30 times per second as a neutron star. The magnetic field also gets compressed, intensifying by factors of trillions. A star with a magnetic field comparable to the sun's ends up with a field strong enough to distort the quantum vacuum. The density alone is mind-bending, but neutron stars possess other properties that strain comprehension. Drop a marshmallow onto a neutron star's surface, and it would impact with the energy of an atomic bomb because the gravity is so powerful. These cosmic remnants spin at incredible speeds, some rotating hundreds of times per second. The fastest known pulsars complete a full rotation in just milliseconds, spinning faster than a kitchen blender. Despite being barely larger than a city, these objects contain more mass than our entire sun, all spinning at velocities that would tear apart any normal matter. The surface gravity on a neutron star is about 200 billion times stronger than Earth's. If you could somehow survive approaching one, and if you were standing on its surface, you would weigh as much as Mount Everest. The escape velocity from a neutron star's surface is about 1/3 the speed of light. Photons climbing out of the gravitational well lose significant energy to gravitational redshift, their wavelength stretching as they struggle against the intense gravity. Time itself runs slower on a neutron star's surface compared to empty space, a consequence of general relativity's prediction that time slows in strong gravitational fields. What creates the extreme magnetism of neutron stars remains partially mysterious, pushing scientific understanding to its limits. As a massive star collapses into a neutron star, its magnetic field gets compressed along with everything else. Like a figure skater pulling in their arms to spin faster, the collapsing star concentrates its magnetic field into a far smaller volume, intensifying it to unfathomable strengths. Combined with the bizarre physics of superdense matter, this creates magnetic fields billions of times stronger than anything we can produce in laboratories. Yet even this explanation is incomplete. Scientists still don't fully understand why some neutron stars become magnetars with fields strong enough to warp the quantum vacuum itself. The strongest magnetars have fields exceeding 10 billion Tesla, strong enough that the quantum vacuum itself behaves differently. In normal space, virtual particle-antiparticle pairs constantly appear and disappear through quantum fluctuations. In magnetar strength fields, these virtual particles become polarized, creating a kind of birefringence where light behaves differently depending on its polarization. The vacuum itself becomes a medium with refractive properties. These cosmic timekeepers are so regular that they rival atomic clocks in their precision, some maintaining accuracy to within microseconds over years of observation. Astronomers use the most stable pulsars as cosmic clocks to test general relativity, search for gravitational waves, and even explore whether fundamental constants change over time.
Some pulsars are so stable that timing them over years allows detection of gravitational waves passing through space, subtly altering Earth's distance from the pulsar. Arrays of pulsars spread across the sky function as a galaxy-sized gravitational wave detector, sensitive to phenomena that individual ground-based detectors cannot observe. When two neutron stars orbit each other, they slowly spiral inward, losing energy to gravitational waves that ripple through the fabric of spacetime itself. Einstein's general relativity predicted these waves a century ago, but they weren't directly detected until 2015, when LIGO observed ripples from colliding black holes. Neutron star binaries emit gravitational waves continuously as they orbit, steadily draining orbital energy and causing them to spiral closer together. Eventually, after millions or billions of years, they collide in a cataclysmic merger that destroys both stars. The impact creates a black hole while simultaneously ejecting clouds of exotic matter into space. These neutron star collisions are believed to be the primary source of heavy elements in the universe, forging gold, platinum, uranium, and other metals in the violence of their final moments. The collision generates temperatures and pressures exceeding those in supernova explosions, allowing nuclear reactions that create elements heavier than iron. Every piece of gold in every ring on Earth was likely created in neutron star collisions billions of years ago, cast into space, and eventually incorporated into the cloud of gas and dust that formed our solar system. In August 2017, gravitational wave detectors observed a neutron star merger for the first time, an event designated GW 170817. Within seconds, gamma-ray satellites detected a burst from the same location. Within hours, telescopes worldwide were observing the fireworks, watching as freshly synthesized heavy elements radioactively decayed and glowed in the infrared. The observations confirmed that neutron star mergers create heavy elements and proved that gravitational waves travel at the speed of light. The collision ejected roughly 10 Earth masses of gold and platinum into space, along with even larger quantities of other heavy elements. The universe might not be alone. Parallel universes, once dismissed as science fiction or the domain of crackpots, have emerged as legitimate possibilities within mainstream physics. Multiple mathematical frameworks suggest that our reality is just one of countless universes existing simultaneously, each with potentially different laws of physics, different histories, and different versions of you. The implications are staggering and deeply unsettling. Everything you are, every choice you've made, every road not taken might exist in some alternate reality. There could be infinite variations of your life playing out across an infinite multiverse, each version experiencing a slightly or radically different existence. Quantum mechanics provides one pathway to multiple universes. At the subatomic level, particles exist in superposition, occupying multiple states simultaneously until measured. An electron can be in two places at once, spinning both clockwise and counterclockwise, existing as both a particle and a wave. This isn't metaphorical. The mathematics of quantum mechanics describes electrons as literally existing in all possible states simultaneously, with each state having an associated probability. When you measure the electron and find it in a specific location, quantum theory suggests the universe splits. There's a branch where you found the electron at position A and another equally real branch where you found it at position B. Both universes continue existing, both versions of you continue their lives, but the complexity of quantum mechanics prevents these branching realities from communicating with each other.
This interpretation, called the many worlds theory, suggests that every quantum event splits reality into multiple branches. Every time a particle's wave function collapses, every time a quantum measurement occurs, the universe multiplies. The number of parallel realities spawned by quantum mechanics would be incomprehensibly vast, increasing exponentially with every passing moment. Right now, as you read this, countless quantum events are occurring in your brain, in the surrounding air, in every atom of matter nearby, each event potentially creating new branches, new universes, new versions of you that made infinitesimally different choices or experienced infinitesimally different random events. Hugh Everett proposed the many worlds interpretation in 1957, and it was initially ridiculed. The idea seemed too extravagant, too metaphysically bizarre to take seriously. But over decades, many physicists have come to accept it as the most straightforward interpretation of quantum mechanics. It solves the measurement problem without requiring mysterious wave function collapse. It eliminates the need for special roles for observers or measurement devices. Everything simply evolves according to the Schrödinger equation, with the universe branching whenever quantum superpositions become entangled with their environment. The many worlds interpretation makes a stunning prediction. Since every quantum outcome occurs in some branch, quantum mechanics doesn't make probabilistic predictions at all. Instead, it describes the structure of the multiverse. When quantum mechanics says an electron has a 70% chance of being found at A and 30% at B, it means 70% of branches contain an observer who found it at A and 30% contain an observer who found it at B. Probability is replaced by branching ratios. You don't have a 70% chance of measuring A. You have certainty that some version of you will measure A, and some version will measure B, with more branches getting A than B. Another route to multiple universes comes from cosmic inflation, the theory that the universe underwent a period of exponential expansion in the first fraction of a second after the Big Bang. Inflation explains many observed features of our universe, like its remarkable uniformity and flatness. When we look at the cosmic microwave background, we see regions that are currently separated by distances so vast that light has never had time to travel between them since the Big Bang. Yet these regions have almost identical temperatures and properties. How did they coordinate to become so similar if they were never in contact? Inflation solves this puzzle. In the universe's first moments, all the regions we can now observe were close together, in thermal contact, able to reach the same temperature. Then, inflation stretched space exponentially, carrying these regions apart faster than light could travel. The expansion was so rapid that regions in thermal equilibrium were suddenly separated by vast distances with no time for light to pass between them. Inflation took a tiny, smooth patch of space and stretched it to encompass the entire observable universe, explaining why distant regions look so similar. But if inflation happened here, it likely happened in other regions of space too. Different regions might have inflated at different rates, creating bubble universes, each potentially with different physical constants and laws. Some of these universes might have stronger or weaker gravity, different subatomic particles, or even different numbers of dimensions. The constants we observe in our universe, things like the strength of electromagnetism or the mass of the electron, might be random variables that take different values in different bubbles. In some bubble universes, the physics might be so different that matter as we know it cannot exist at all. Eternal inflation models suggest that once inflation starts, it can never completely stop. While inflation ends in some regions, creating bubble universes like ours, it continues in other regions, spawning new bubbles eternally. The multiverse grows without bound, producing infinite bubble universes with every possible combination of physical parameters. Somewhere in this infinite ensemble, there are identical bubbles to ours, bubbles where Earth exists and your exact duplicate lives an identical life. There are bubbles where Earth never formed, bubbles where life never evolved, bubbles where dinosaurs still rule, bubbles where humans developed radically different civilizations. Then there's the mathematical inevitability argument. If space is infinite and matter is finite, then there are only so many ways that matter can arrange itself in any given volume. The number of possible arrangements is astronomically large, but still finite. Consider a volume of space 1 billion light-years across. Within that volume, there are perhaps 10 to the 80th atoms, arranged in specific configurations that create galaxies, stars, planets, and possibly life. The number of ways these atoms could be arranged is enormous, maybe 10 to the power of 10 to the 80th, but it's still a finite number. In an infinite universe with finite matter density, every possible arrangement must eventually repeat. Somewhere out there, infinitely far away, there must be an exact duplicate of this volume of space with atoms arranged identically. There must be another Earth, another you, reading these exact words at this exact moment. In fact, there must be infinite duplicates, and between the exact copies, there must be countless near copies. Copies. Versions of you with subtle or major differences in life circumstances. There are versions where you made different career choices, versions where you live in different cities, versions where you were never born. The patchwork multiverse arising from mathematical inevitability is perhaps the most philosophically disturbing version. Unlike quantum many worlds where branches are fundamentally separate, or inflation bubbles that might have different physics, patchwork duplicates exist in the same universe with the same physics. They're just really, really far away. In principle, you could travel to meet your duplicate if you had a spaceship capable of crossing incomprehensible distances. Of course, the distance is so vast that the journey would take far longer than the current age of the universe, even at light speed, making such meetings impossible in practice. Evidence for multiple universes remains frustratingly indirect, but some researchers claim to have found tantalizing hints. Laura Mersini-Houghton predicted that if our universe is quantum entangled with other universes in the multiverse, it should leave a specific signature in the cosmic microwave background, the faint afterglow of the Big Bang that permeates all of space. She predicted a cold spot, a region roughly 10 degrees across, where the microwave background appears slightly cooler than expected. This cold spot could be a bruise left by our universe colliding with another bubble during inflation, or it could be evidence of quantum entanglement with other universes that pulls energy out of specific regions. 7 months after making this prediction, astronomers announced they had found exactly such a cold spot using data from NASA's WMAP satellite. The cold spot appears in the constellation Eridanus, a region about 10 degrees across where the cosmic microwave background is about 70 microkelvins cooler than surrounding areas. While other explanations exist, including the possibility that it's just a statistical fluke or evidence of a massive supervoid in the foreground, Mersini-Houghton argues this could be evidence of our universe overlapping with another, a place where two bubbles in the cosmic foam briefly touched.
Gravitational waves offer another potential window into the multiverse. These ripples in space-time were first directly detected in 2015 when LIGO observed waves generated by colliding black holes. The detection opened a new era of gravitational wave astronomy, allowing observation of cosmic phenomena invisible to electromagnetic telescopes. If cosmic inflation occurred, it should have generated gravitational waves in the universe's first moments. These primordial gravitational waves would still be propagating through space, potentially detectable by sufficiently sensitive instruments. Finding them would strengthen the case for inflation, which in turn supports the bubble universe model. Each piece of evidence adds another layer to a picture of reality far stranger than previous generations imagined. Future gravitational wave detectors might detect signatures of bubble collisions, direct evidence of other universes impacting our own during inflation. Such a discovery would revolutionize our understanding of reality, confirming that our universe is just one of many, and opening questions about whether we could ever communicate with or visit these other cosmic domains. The philosophical and existential implications of the multiverse are profound. If infinite universes exist, containing every possible variation of history, then every choice you make is ultimately meaningless on the cosmic scale, because all possible choices get made in other universes. There's a universe where you made the opposite decision, and another where you did something completely different. This could be seen as deeply nihilistic. If all possibilities are realized somewhere, what's the point of choosing? How can any action matter if every alternative also occurs? Yet, this doesn't diminish the importance of your choices in this reality, the one you're actually experiencing. Even if infinite versions of you exist elsewhere, you only experience one timeline, one sequence of moments. Your choices still matter to you and the people in your universe, even if somewhere else, other versions of you made different choices. The multiverse doesn't make morality or meaning impossible. It just relocates them from the cosmic scale to the personal scale. Your life matters, even if it's one of infinite variations, because it's the only one you'll experience.
The multiverse might even explain why our universe seems so precisely tuned for life. The physical constants governing our reality appear fine-tuned to allow complex chemistry and biology to exist. If gravity were slightly stronger, stars would burn out too quickly for life to evolve. If the electromagnetic force were different, atoms couldn't form stable molecules. The strong nuclear force must be precisely calibrated to allow carbon synthesis in stars. Change any of these constants by even a few percent, and the universe becomes lifeless. This apparent fine-tuning has puzzled scientists for decades. Why do the constants have exactly the values they need for life to exist? Some see this as evidence for intelligent design, suggesting the universe was deliberately crafted to support life. But in a multiverse containing every possible set of physical laws, there's no puzzle. Most universes would be sterile, incapable of supporting any form of complexity. We exist in one of the rare universes where the laws permit life simply because we couldn't exist anywhere else. It's a selection effect, the anthropic principle in action. We find ourselves in a life-supporting universe because that's the only type of universe where observers can exist to ask the question. Our planet is spinning faster, and nobody is entirely sure why. In 2021, scientists measuring Earth's rotation with atomic precision discovered that days were averaging 0.05 milliseconds shorter than expected. This might sound trivial, but it represents a reversal of a multi-billion-year trend. Since Earth's formation, its rotation has been gradually slowing down, primarily due to tidal forces from the Moon. 3.5 billion years ago, when life was just beginning to emerge in Earth's oceans, a day lasted only 12 hours. The lengthening has been steady and predictable for eons. Now, suddenly, Earth is speeding up instead. The moon's gravitational pull creates tidal bulges in Earth's oceans. As Earth rotates beneath these bulges, friction between the moving water and the ocean floor drains rotational energy from Earth and transfers it to the moon's orbit. This process causes Earth's rotation to slow gradually, while the moon drifts away at about 3.8 centimeters per year. Eventually, billions of years from now, if the sun doesn't engulf both bodies first, Earth would become tidally locked with the moon, always showing the same face to our satellite, just as the moon currently always shows the same face to Earth.
A faster spinning Earth might seem an abstract concern, but it carries real consequences for our technological-dependent civilization. GPS satellites rely on incredibly precise timing to function. They continuously broadcast their position and the exact time, synchronized to atomic clocks accurate to nanoseconds. Receivers on Earth calculate their location by measuring how long signals take to arrive from multiple satellites, using the time delay to determine distance. This method requires extreme timing precision. If Earth's rotation falls out of sync with atomic time by even milliseconds, the calculated satellite positions become incorrect. Navigation systems fail. Cell phone towers lose synchronization. Computer networks relying on precise timestamps experience errors. Financial markets that depend on synchronized timestamps for high-frequency trading face chaos. Power grids that synchronize across continents lose coordination. The entire infrastructure of modern technological civilization depends on precise timekeeping. By 2030, if the acceleration continues unchecked, we could face a full-scale technological meltdown as the discrepancy between atomic time and Earth's actual rotation grows too large to ignore. Fortunately, timekeepers have a solution, though it's only a temporary fix. Leap seconds can be added or subtracted from international atomic time to keep our clocks synchronized with Earth's actual rotation. When Earth's rotation runs slow, a leap second is added, usually on June 30th or December 31st. When Earth speeds up, a negative leap second could theoretically be subtracted, though this has never been necessary in the era of atomic timekeeping. These adjustments are announced 6 months in advance by the International Earth Rotation and Reference Service, giving computer systems time to prepare. But leap seconds themselves create problems, as demonstrated by widespread internet outages and computer glitches that have occurred when they're implemented. In 2012, major websites including Reddit, LinkedIn, and Foursquare experienced outages when a leap second caused software bugs in Linux systems. Airlines reported reservation system failures. The problem is that many computer systems are poorly equipped to handle time going backward, or a minute lasting 61 seconds instead of 60. Some engineers are lobbying to eliminate leap seconds entirely, allowing atomic time and Earth's rotation to gradually drift apart. This would simplify computer systems, but would mean that eventually, centuries from now, noon might occur in the middle of the night, the sun directly overhead at times we call the small hours of morning. The cause of Earth's current acceleration appears to be climate change, specifically the melting of ice at the poles. Water has a peculiar property where it expands when it freezes, which is why ice floats and why frozen pipes burst. Glaciers and ice sheets are essentially frozen water spread over vast areas and stacked into towering formations kilometers thick.
Greenland's ice sheet contains enough frozen water to raise global sea levels by 7 meters if it melted completely. Antarctica holds enough to raise sea levels by 58 meters. As global temperatures rise and this ice melts, it flows closer to Earth's surface and toward the oceans. This redistribution of mass affects Earth's rotation through the conservation of angular momentum. Like a figure skater pulling their arms inward to spin faster, Earth spins more quickly when mass moves closer to its axis of rotation. The melting ice caps are inadvertently causing the planet to accelerate. Ice that was spread across high latitudes and stacked kilometers thick is melting into water that flows toward lower latitudes and spreads across the ocean's surface, moving mass closer to Earth's rotational axis and speeding up the planet's spin. But this acceleration is likely temporary. The moon's gravitational pull on Earth's oceans creates tides, and this tidal interaction slowly transfers rotational energy from Earth to the moon's orbit. As Earth loses rotational energy, it spins more slowly, while the moon gradually drifts farther away at a rate of about 3.8 centimeters per year. This has been measured precisely using laser ranging experiments where powerful laser pulses are fired at retroreflectors left on the moon by Apollo astronauts. By measuring the time it takes light to make the round trip, scientists can determine the moon's distance to centimeter precision and track how it changes over time. Eventually, billions of years from now, Earth would become tidally locked with the moon, always showing the same face to our satellite, just as the moon currently always shows the same face to Earth. At that point, the moon would hang motionless in the sky as seen from one hemisphere of Earth, while being forever invisible from the other hemisphere. Days would last about 47 current days, matching the orbital period of the moon. But this future will never arrive because the sun will expand into a red giant in about 5 billion years, likely engulfing both Earth and the moon before tidal locking completes. The current climate-driven speed-up is a blip in this longer trend towards slower rotation. Climate models suggest the melting will continue for centuries, perhaps causing Earth to spin measurably faster over that time. But eventually, whether through human intervention halting climate change or natural processes reaching a new equilibrium, the melting will stop. When it does, the moon's tidal braking will resume its dominance, and Earth's rotation will return to its long-term pattern of slowing down. The melting ice has another concerning consequence beyond affecting Earth's spin. As ice melts and flows toward the oceans, it doesn't distribute evenly. The water tends to accumulate at the equator due to centrifugal force from Earth's rotation. This creates what's called equatorial bulging, effectively adding more water to Earth's spare tire. The equatorial bulge already exists due to centrifugal force, making Earth slightly oblate, wider at the equator than at the poles by about 43 kilometers. But adding more water to the bulge means sea levels will rise more at the equator than at the poles.
Coastal regions near the equator will experience higher sea level rise than current models predict. Additionally, more water at the equator means more water vapor in the atmosphere there, potentially intensifying tropical storms, hurricanes, and typhoons that form in equatorial regions. These storms draw their energy from warm ocean water. More water means a larger heat reservoir to fuel storm formation. Higher sea surface temperatures combined with more available moisture could create storms of unprecedented intensity. Climate models are struggling to keep pace with observed changes. The Arctic is warming roughly 3
times faster than the global average, a phenomenon called Arctic amplification. Ice reflects sunlight, while open ocean absorbs it, creating a positive feedback loop where melting ice exposes dark water that absorbs more heat, causing more melting. This feedback is accelerating the loss of Arctic ice sea beyond initial predictions. Summer ice extent in the Arctic has decreased by about 40% since satellite observations began in the late 1970s, and some models suggest ice-free Arctic summers could occur within decades. Jupiter's auroras are the most spectacular light shows in the solar system, dwarfing anything we see on Earth. These massive displays cover areas larger than our entire planet, pulsing with terawatts of power, enough energy to briefly supply all of human civilization. They never stop, rippling perpetually across Jupiter's poles in shimmering curtains of light visible across the solar system. The auroras extend hundreds of kilometers above Jupiter's cloud tops, creating glowing ovals that could swallow Earth whole. For centuries, these auroras were mysterious, their mechanisms unknown. Then, in 2016, NASA's Juno spacecraft arrived in Jupiter's orbit and began revealing the secrets behind these cosmic fireworks displays. On Earth, auroras are created when solar wind particles enter our atmosphere and interact with our magnetic field. Charged particles spiral along magnetic field lines toward the poles, where they collide with atmospheric gases, causing them to glow. Oxygen collisions produce green and red light. Nitrogen creates blue and purple. The intensity varies with solar activity, with the most spectacular displays occurring during geomagnetic storms when the sun releases coronal mass ejections directly at Earth.
Jupiter's auroras operate on a similar principle, but at an incomprehensibly larger scale. Jupiter's magnetosphere is 20,000 times stronger than Earth's and extends so far into space that it might reach all the way to Saturn's orbit, about 600 million kilometers from Jupiter. This gigantic magnetic bubble captures particles from across the solar system, funneling them toward Jupiter's poles, where they create the planet's permanent auroras displays. Unlike Earth, where auroras are intermittent and dependent on solar activity, Jupiter's auroras never stop. They're powered primarily by the planet's rotation rather than solar wind. But magnetic fields alone don't explain Jupiter's auroras. The true power source lies deep within the planet's interior, in a form of matter so exotic it seems like science fiction. Jupiter is a gas giant composed primarily of hydrogen and helium. There's no solid surface. If you fell into Jupiter, you would descend through ever denser layers of gas that gradually transition into liquid under increasing pressure. Deep within the planet's core, perhaps 50,000 kilometers below the cloud tops, the immense pressure transforms hydrogen into something impossible under normal conditions. It becomes metallic, liquid metallic hydrogen. Scientists recreated this transformation in laboratories by firing 160 laser beams on a tiny sample of liquid hydrogen, subjecting it to pressures comparable to Jupiter's interior. The target contained about 20 millionths of a gram of hydrogen, less than a speck of dust, but when hit with laser pulses delivering 500 times the power consumption of the entire United States, focused onto that microscopic target for a few nanoseconds, the hydrogen underwent a surreal phase transition. Under these extreme conditions, hydrogen's structure fundamentally changes. It becomes opaque, reflective, electrically conductive,
a shiny liquid metal where normal hydrogen once existed. If we could somehow journey to Jupiter's core and survive the crushing pressure and searing heat, we would see a deep ocean of fluid, shiny, metallic hydrogen stretching for thousands of kilometers in every direction. This ocean is in constant motion, swirling with currents driven by Jupiter's rotation and internal heat. Because metallic hydrogen conducts electricity like copper or aluminum, these moving currents generate electrical fields and magnetic fields through the same dynamo process that powers Earth's magnetic field, but on a vastly larger scale.
This material doesn't fall back to Io's surface. Instead, it gets captured by Jupiter's magnetic field, forming a torus of charged particles that orbits Jupiter at Io's distance. This Io plasma torus contains ions of sulfur and oxygen stripped from volcanic gases, creating a donut-shaped cloud of glowing plasma around Jupiter. As charged particles from the torus spiral along magnetic field lines toward Jupiter's poles, they create additional light shows, supplementing the auroras powered by solar wind and Jupiter's internal processes. The combination creates aurora displays unmatched anywhere else we've observed. Some of Jupiter's auroral features are directly linked to specific moons. Io, Europa, and Ganymede each create distinct auroral footprints on Jupiter, bright spots that mark where magnetic field lines connected to these moons intersect Jupiter's atmosphere. These footprints move across Jupiter's poles as the moons orbit, creating dynamic patterns. By studying these moon-induced auroras, scientists can learn about the moon's own magnetic properties and internal structures. One mystery that puzzled scientists for years was why Jupiter's auroras pulse with such regularity, flashing every 27 minutes like cosmic clockwork. Earth's auroras flicker and dance unpredictably, responding to chaotic variations in solar wind. But Jupiter's auroras show periodic brightenings that occur with remarkable precision. By analyzing data from Juno and the European Space Agency's XMM Newton telescope, which observes X-ray emissions from the auroras, researchers discovered that periodic vibrations crash across the magnetosphere like waves on an ocean. These vibrations send heavy ion particles surfing along magnetic field lines toward Jupiter, where they bombard the atmosphere and create the pulsing aurora displays. The ions, primarily from Io's volcanic emissions, get accelerated to enormous energies by the vibrating magnetic field, then crash into Jupiter's atmosphere at the poles. When they collide with hydrogen atoms in the upper atmosphere, they create X-ray emissions that brighten and dim with the 27-minute period. But what causes these regular vibrations remains unknown. Why does Jupiter's magnetosphere ring like a bell every 27 minutes? What determines this specific rhythm? Some researchers suggest the vibrations might be driven by the solar wind, which could set up standing waves in the magnetosphere. Others propose internal processes within Jupiter itself might trigger the pulsations. The mystery is partially solved, but not fully understood. Each answer reveals new questions, a common pattern in planetary science. The study of Jupiter's magnetosphere and auroras has practical applications beyond pure science. Understanding how planetary magnetic fields interact with charged particles helps protect satellites and astronauts from radiation. Jupiter's radiation belts are so intense they would kill an unprotected human within minutes and can damage even hardened spacecraft electronics. Learning how these radiation belts form and evolve helps engineers design better shielding for future missions. Space surrounding Earth is filling with trash, and we're running out of time to address it. Nearly everything humanity has launched into orbit since Sputnik in 1957 is still there, circling our planet at tremendous speeds. Over 130 million pieces of space junk currently orbit Earth, from defunct satellites the size of buses to fragments smaller than ball bearings created by collisions in anti-satellite weapon tests. This debris field is growing rapidly as commercial space companies launch constellations of thousands of new satellites, some companies planning networks of tens of thousands.
Each junk is a potential catastrophe waiting to happen because orbital velocities are so extreme that even tiny fragments carry devastating energy. Objects in low Earth orbit travel at about 7.8 kilometers per second, roughly 28,000 kilometers per hour. At these speeds, kinetic energy increases with the square of velocity, so even small objects pack enormous punch. A paint fleck traveling at orbital velocity carries as much energy as a bowling ball dropped from a building. A ball bearing has the impact energy of a small car at highway speed. Larger debris can hit with the force of bombs. In 2009, NASA actually had to order an emergency evacuation of the International Space Station when they discovered a piece of space junk about the same size as a CD traveling towards them at 8 kilometers per second. The astronauts hadn't trained for this specific scenario. They received the warning with less than 12 hours' notice, barely enough time to prepare. The crew sealed off sections of the station to limit potential air loss, then retreated to the Soyuz spacecraft docked at the station. If the debris struck, they could undock and return to Earth immediately. Chaos erupted as they worked through emergency procedures, closing hatches, powering down non-essential systems, preparing for potential impact. The debris passed within a few hundred meters of the station, close enough that if its trajectory had been slightly different, disaster would have occurred. Fortunately, the debris missed, but the incident highlighted how vulnerable the station is to orbital debris and how little warning time exists to respond to threats. If the debris had struck, the results would have been catastrophic. Even something as small as the debris that threatened the ISS, traveling at 8 kilometers per second, carries tremendous energy. The ISS is pressurized to Earth's sea-level atmospheric pressure, about 100 kilopascals. The station's hull is designed to withstand micrometeorite impacts with multiple layers of protection, but it's not invulnerable. A piece of debris punching through the hull would create explosive decompression. The pressure differential would force air out through the hull at tremendous speed, creating hurricane-force winds inside the module.
Laboratory simulations demonstrate the terrifying power of orbital debris. Researchers fire tiny projectiles at satellites or satellite components using gas guns that accelerate objects to hypersonic speeds. High-speed cameras record the impacts, capturing the collision in microsecond detail. A fragment smaller than a pill, weighing just 250 milligrams, punches through aluminum panels like they're tissue paper when traveling at 14 kilometers per second. The projectile vaporizes instantly on impact, creating a superheated plasma that explosively expands. Secondary fragments spray in all directions, each one a potential projectile. The primary target is destroyed instantly, transformed from functional hardware into twisted wreckage and a cloud of high-velocity fragments. A single collision can generate thousands of new pieces of debris, each one a lethal projectile capable of causing further collisions. This creates the nightmare scenario known as Kessler syndrome, named after NASA scientist Donald Kessler, who first described it in 1978.
Kessler syndrome is a cascade effect where each collision creates more debris, which causes more collisions, exponentially increasing the amount of junk in orbit until entire altitude ranges become unusable. The mathematics of Kessler syndrome are sobering. Once debris density reaches a critical threshold, collisions become self-sustaining. Even if we stopped launching anything new, collisions between existing debris would continue generating more fragments faster than atmospheric drag removes them. The debris population would grow exponentially, creating an impenetrable shell of high-velocity shrapnel around Earth. Specific orbits, particularly the heavily used low Earth orbit altitude of 800 to 1200 kilometers, are approaching this critical density. Some forecasts suggest that a major collision between large pieces of debris could happen once every 5 years on average. And we see thousands upon thousands of near misses every single day as a result of all the junk that we put up there. Satellites routinely perform collision avoidance maneuvers using onboard thrusters to dodge predicted close approaches. The International Space Station maneuvers several times per year to avoid debris. Each maneuver consumes propellant, requires crew time to prepare, and disrupts ongoing experiments. The threat isn't just to satellites and spacecraft. Our modern civilization depends on orbital infrastructure in ways most people don't realize. GPS navigation guides aircraft, ships, cars, and smartphones. Weather forecasting relies on meteorological satellites that monitor atmospheric conditions globally. Telecommunications satellites relay phone calls, television broadcasts, and internet data across continents and oceans. Earth observation satellites monitor agriculture, track deforestation, detect wildfires, measure sea level rise. Financial markets depend on satellite communications for high-frequency trading. Power grids use GPS timing signals to synchronize across regions. If a cascade of collisions destroyed significant numbers of satellites, it would cripple global infrastructure. Ships and aircraft would lose navigation capabilities, forced to rely on older, less precise systems. Weather services would lose forecasting ability, unable to predict hurricanes and severe storms days in advance. Communications networks would fragment, especially in remote regions where satellites provide the only connectivity. Financial markets would struggle to coordinate transactions across exchanges. Military forces would lose surveillance and communication capabilities. The damage wouldn't be limited to space. It would ripple through every aspect of modern life on Earth's surface. The economic cost has been estimated in trillions of dollars, potentially triggering global recession. The loss of weather satellites alone would cost agricultural industries billions in reduced crop yields due to inability to predict optimal planting times and severe weather. Aviation would face massive disruptions, potentially grounding flights in regions without adequate ground-based navigation systems.
Tracking space debris is the first step toward managing this threat, but current capabilities are severely limited. The U.S. Air Force, through its Space Surveillance Network, has been cataloging space junk since the early 1980s. The network includes ground-based radars and optical telescopes spread across the globe, continuously scanning the sky for objects. They started with 6,000 cataloged objects and had grown to 10,000 over the next 2 decades as tracking improved and the debris population increased. Since 2009, the amount of trackable space junk has gone up by 20% to over 25,000 pieces.
But tracking systems can only detect objects larger than about 10 centimeters in low Earth orbit or about 1 meter in geostationary orbit. The millions of smaller fragments flying through orbit remain invisible to current technology, too small for radars to detect and too faint for optical telescopes to see against the bright Earth background. These tiny pieces can still be lethal. A fleck of paint traveling at orbital velocity once cracked the windshield of Space Shuttle Challenger during the STS-7 mission in 1983. The impact crater was almost a quarter-inch wide, caused by a paint chip estimated at just a few tenths of a millimeter across. This demonstrated that size doesn't correlate with danger when objects are moving at multiple kilometers per second. Even microscopic debris can damage spacecraft, pitting solar panels, degrading optical surfaces, and potentially puncturing pressurized modules. Statistical models estimate the debris population by analyzing the trackable objects and extrapolating to smaller sizes. These models suggest there are roughly 34,000 objects between 1 and 10 centimeters, around 900,000 objects between 1 millimeter and 1 centimeter, and over 130 million objects smaller than 1 millimeter. Each debris event, whether a collision or satellite breakup, adds thousands or millions of new fragments, depending on the masses involved and collision energy. Proposed solutions to the space junk crisis range from practical to bizarre. One approach involves space harpoons, devices that would spear pieces of debris and drag them out of orbit to burn up safely in Earth's atmosphere. The Remove Debris satellite, launched to the International Space Station in 2018, successfully tested both a harpoon and a net in orbit, demonstrating that capturing debris is technically feasible. The harpoon fired into a target panel at 10 meters distance, penetrating the aluminum and proving that tethered retrieval could work. Another idea uses giant nets to capture defunct satellites, bundling them up for deorbiting. The net would be fired at the target, wrapping around it and cinching tight. Then a tether would drag the ensnared satellite down into the atmosphere, where it would burn up. This method works well for large, intact objects, but struggles with debris clouds of fragments. Magnetic tethers could attach to metal debris, particularly rocket bodies and satellites made of aluminum or steel, and slow them down through electromagnetic interactions with Earth's magnetic field. Some proposals involve lasers, either ground-based or space-based, that would vaporize small pieces of debris or alter their trajectories. A sufficiently powerful laser could ablate material from a debris object's surface, creating thrust that changes its orbit. Ground-based lasers have the advantage of not adding more mass to orbit, but face challenges with atmospheric distortion and weather. Space-based lasers avoid atmospheric problems, but require launching and maintaining complex systems in the debris-filled environment they're trying to clean. One of the more unusual proposals involves using foam or aerogel to capture debris. A spacecraft would deploy large volumes of low-density foam that would gently slow down small debris objects through drag, causing them to deorbit naturally. The foam would eventually re-enter and burn up, taking the captured debris with it. This method could potentially capture many small pieces simultaneously, but faces challenges with deployment and ensuring the foam doesn't become a debris hazard itself. There's also the paintball proposal, one of the most creative suggestions. Shooting debris with paintballs serves two purposes. First, the impact itself imparts momentum, altering the debris's trajectory. Second, coating the debris with white reflective paint increases the force from sunlight, which at orbital altitudes actually exerts measurable pressure on objects. This solar radiation pressure would gradually push painted debris toward lower orbits where atmospheric drag would finish the job.
The downside is that this would need about 20 years to work, requiring very long-term planning. Each solution faces enormous technical and economic challenges. Cleaning up space is expensive, and removing debris piece by piece is agonizingly slow. Even if we could remove 100 pieces of debris per day, it would take over 680 years to clear just the 25,000 trackable objects, and by then, collisions would have created far more. The economics are daunting. Estimates suggest removing a single large debris object might cost tens of millions of dollars. Multiplying that across thousands of objects makes comprehensive cleanup economically prohibitive with current technology. The international legal framework surrounding space debris is inadequate for the challenge we face. Current space law, primarily the Outer Space Treaty of 1967, dates from an era when only a handful of nations had space programs and satellites were rare, expensive assets. The treaty establishes that nations retain jurisdiction over objects they launch, regardless of whether those objects are still functional. A satellite launched decades ago that's now dead and tumbling through orbit is still legally the property of the country that launched it, even though it's become a hazard.
This creates legal complications for debris removal. Touching another nation's satellite without permission, even to remove it as debris, could be considered an act of aggression or theft. There's no international agreement on who's responsible for cleaning up debris or who would pay for removal efforts. Some countries have voluntarily adopted guidelines for reducing debris creation, like deorbiting satellites at end of life, but these are not legally binding and compliance varies. The lack of international cooperation on space debris mirrors failures to address other global commons problems like ocean pollution and climate change. Each nation acts in its short-term interests, launching satellites and occasionally creating debris through anti-satellite tests, while the collective long-term cost accumulates. Several nations have conducted anti-satellite weapon tests that created thousands of trackable debris pieces. China's 2007 test alone created over 3,000 cataloged fragments and an estimated 150,000 pieces too small to track. If we fail to address space debris, we risk losing access to Earth's orbit entirely. Kessler syndrome could make it impossible to safely operate satellites in the most useful orbits, particularly the low Earth orbit region, where most satellites operate and where debris density is highest. Space stations would become untenable, too dangerous to maintain with crew aboard. Launching anything through the debris field would be suicidally dangerous, like flying an aircraft through a hailstorm of bullets moving at 10 times the speed of sound. Future generations might look at satellites the way we look at ancient astronomical instruments, evidence of past capabilities we've lost. The night sky, which has inspired humanity throughout history, would become a cosmic junkyard, visible as thousands of tumbling, glinting objects crossing overhead. The dream of space exploration and settlement would die before it truly began, killed by our inability to manage the waste products of our first tentative steps into the cosmos.
Preventing this outcome requires international cooperation, better tracking, active debris removal, and stricter regulations on what can be launched and how satellites are deorbited at end of life. Some progress is being made. New satellites are increasingly designed with deorbit capabilities, including propulsion systems to lower their orbits at end of life, or mechanisms to deploy drag sails that accelerate atmospheric re-entry.
But these measures only address future satellites, not the legacy population already in orbit. The challenge is urgent. Every year we delay implementing comprehensive debris mitigation and removal measures, the problem worsens. Collisions continue creating new debris. More satellites launch into already crowded orbits. The critical density threshold approaches. Once Kessler syndrome begins in earnest, stopping it might be impossible. The debris cascade could render low Earth orbit unusable for generations, potentially centuries, until atmospheric drag slowly clears the debris. We have a brief window to act before we lock ourselves out of space for the foreseeable future. Signals from deep space are triggering serious scientific investigation into whether we're being contacted by alien civilizations. Fast radio bursts, mysterious pulses of radio energy so bright they can't originate from Earth, arrive from various points across the sky with no warning. When Duncan Lorimer first detected one in 2007, it was so unprecedented that he questioned whether his equipment was malfunctioning. The signal was impossibly bright, apparently originating from billions of light years away, yet concentrated into a flash lasting just 5 milliseconds. Nothing in conventional astrophysics could explain such a phenomenon. The burst released as much energy in 5 milliseconds as the sun emits in an entire day, but compressed into radio wavelengths. The signal swept across a wide range of frequencies, from low to high, with lower frequencies arriving slightly later than higher ones. This dispersion indicates the signal traveled through ionized gas, the intergalactic medium, for billions of years before reaching Earth. By measuring the dispersion, astronomers calculated the distance to the source, finding it lay in a galaxy roughly 3 billion light-years away.
For a moment, the possibility seemed real. This could be a signal from an extraterrestrial civilization, perhaps a powerful beacon or transmission from an advanced technology. The energy levels seemed too extreme for natural processes, and the brief duration suggested something artificially generated rather than a continuous astrophysical source. But the signal didn't repeat, making further study impossible. Was it real? Was it a glitch? With only one detection, certainty proved elusive. The search for alien intelligence has a long and often secret history. In 1961, astronomer Frank Drake organized a clandestine meeting of scientists who believed that technological civilizations must exist elsewhere in the universe. Meeting at the National Radio Observatory in Green Bank, West Virginia, this group included some of the era's most prominent astronomers and physicists. They called themselves the Order of the Dolphin, chosen because dolphins represent non-human intelligence on Earth. Drake presented an equation, now called the Drake equation, for estimating the number of detectable civilizations in our galaxy. The equation multiplies several factors: the rate of star formation, the fraction of stars with planets, the number of habitable planets per system, the fraction where life develops, the fraction where intelligence evolves, the fraction that develop detectable technology, and the average time such civilizations remain detectable. By making optimistic assumptions about each factor, they calculated that roughly 10,000 detectable civilizations should exist in the Milky Way alone. This number energized the search, suggesting finding alien signals was just a matter of looking hard enough in enough places at enough frequencies. If 10,000 civilizations exist in our galaxy of 400 billion stars, then roughly 1 in 40 million stars hosts a detectable civilization. Challenging odds, but not hopeless. If we could search millions of stars across thousands of frequency channels, we should eventually find something.
The first potential alien signal appeared in 1977 when the Big Ear radio telescope in Ohio detected a powerful narrowband radio transmission lasting 72 seconds. The signal was so strong and unusual that astronomer Jerry Emin, reviewing computer printouts of the observation, scribbled "Wow" in the margin, giving the signal its famous name. What made it compelling was its frequency, 1,420 megahertz, the hydrogen line. This is the natural frequency at which hydrogen atoms emit and absorb radiation. Astronomers had long predicted that aliens would use the hydrogen line if they wanted to be detected because it's naturally significant in the universe. Hydrogen is the most abundant element, and any civilization that develops radio astronomy would quickly discover the hydrogen line. It's a logical frequency for interstellar communication, a natural meeting place in the radio spectrum. The WOW signal appeared at exactly this frequency, as if deliberately chosen to attract attention. For years, the WOW signal remained unexplained, a tantalizing hint that we might not be alone, but it never repeated. Big Ear pointed at the same region of sky again and again, finding nothing. Other telescopes searched the area with no success. Eventually, astronomer Antonio Paris proposed that the signal came from a comet, specifically 266P Christensen, which was in the observed region, though unknown at the time of the original detection. When Paris observed this and similar comets, he detected hydrogen line emissions matching the WOW signal's characteristics. The explanation remains controversial. Some researchers point out that comets hadn't been observed producing such strong hydrogen line emissions before, and that the original signal showed characteristics inconsistent with a moving comet. The mystery of the WOW signal persists, though most astronomers now favor natural explanations over extraterrestrial ones. Then, in 2007, came a detection of what would become one of the biggest mysteries in physics, something that could have been a game-changer in the search for aliens. Duncan Lorimer's team, analyzing archival data from the Parkes Radio Telescope in Australia, found the burst that would bear Lorimer's name. After the initial shock and verification that the signal was real and not instrumental artifact, astronomers began searching for more fast radio bursts. They found them. Telescopes around the world started detecting similar bursts, each lasting milliseconds, each releasing tremendous energy, each originating from cosmological distances. By 2023, thousands of fast radio bursts had been cataloged. They were coming from all over the sky, from different galaxies billions of light years away, with no apparent pattern or preferred direction. Clearly real, clearly astrophysical, but what were they? The all-sky distribution meant they probably weren't artificially generated. If aliens were responsible, they would have to be everywhere, scattered across the entire observable universe, all using the same signaling method. That seemed implausible. If one civilization developed radio technology, why would thousands of unrelated civilizations across billions of light years independently choose to generate identical signals? Natural phenomena became the more probable explanation, but identifying the source remained challenging. Neutron star collisions emerged as one leading candidate for fast radio burst origins. When two neutron stars spiral together and merge, they release tremendous energy across the electromagnetic spectrum, including potentially brief radio flashes. The energetics match what's observed in fast radio bursts. The duration of the pulses, just milliseconds, fits the expected timescale of merger events, where objects kilometers in size collide at significant fractions of light speed. The collision would be over in an instant, potentially producing a bright radio flash that could be detected across billions of light years.
Another possibility involves magnetars, neutron stars with extreme magnetic fields. Recently, astronomers detected a fast radio burst originating from a known magnetar in our own Milky Way galaxy, SGR 1935-2154. In April 2020, this magnetar produced a burst that was detected by multiple radio telescopes worldwide. The burst wasn't as bright as extragalactic fast radio bursts, but scaled for distance, the energy output matched. This strongly suggested that at least some fast radio bursts come from magnetars. But magnetars doing what exactly? The leading theory involves magnetic reconnection, where twisted magnetic field lines snap and reconnect, releasing energy. On a magnetar with magnetic fields billions of times stronger than Earth's, this process could accelerate particles to relativistic speeds and generate brief but intense radio emission. Starquakes on magnetars, sudden shifts in the crust, might trigger fast radio bursts by disturbing the magnetosphere and causing particle acceleration. While this makes fast radio bursts less likely to be alien signals, it reveals another layer of extreme physics in the universe. Magnetars are pushing matter and energy to limits we can barely comprehend, creating phenomena that stretch our theoretical understanding. Even if they're not messages from ET, they're fascinating laboratories for studying physics under conditions impossible to replicate on Earth. Despite these natural explanations, the search for extraterrestrial intelligence continues with renewed vigor. The Breakthrough Listen project, funded by entrepreneur Yuri Milner, represents the most comprehensive search ever conducted. Using the world's largest radio telescopes, including the Green Bank Telescope in West Virginia and the Parkes Telescope in Australia, Breakthrough Listen scans millions of stars across billions of frequency channels, looking for artificial signals amid the cosmic noise.
The project also conducts optical searches, using telescopes equipped with high-speed cameras to look for brief laser pulses from nearby stars. An advanced civilization might use powerful lasers for interstellar communication, sending brief but intense flashes that could be detected across light years. These optical SETI searches complement radio observations, covering different parts of the electromagnetic spectrum where aliens might choose to transmit. Researchers analyze the atmospheres of distant exoplanets, looking for chemical signatures that might indicate life or even industrial activity. The James Webb Space Telescope, launched in 2021, can detect atmospheric composition of planets orbiting nearby stars, potentially revealing biosignatures like oxygen and methane in thermodynamic disequilibrium, which on Earth is maintained by life. Even more speculatively, Webb might detect technosignatures, chemicals that indicate industrial processes like chlorofluorocarbons that don't occur naturally but are produced by technology. The philosophical implications of finding or not finding alien intelligence are profound. If we discover that we're alone in the universe, it suggests something went catastrophically wrong in our assumptions. Perhaps life is far rarer than we think, requiring such specific conditions that Earth is genuinely unique among trillions of planets. Maybe intelligence is a cosmic fluke that almost never evolves, with humans being extraordinarily lucky beneficiaries of billion-year chains of improbable events. Perhaps civilizations typically destroy themselves before becoming detectable, trapped in some great filter that we've yet to encounter. This is among the most disturbing possibilities. If there are 10,000 civilizations capable of radio communication,
location in our galaxy, but they all destroy themselves within decades or centuries of developing that capability, we would never detect them. And it would suggest we're headed for the same fate, doomed by the same forces that destroyed countless predecessors. Alternatively, finding alien signals would shatter our understanding of our place in the cosmos. We would no longer be special, unique, or central to existence. We'd be one species among potentially millions, possibly unremarkable or primitive compared to civilizations that have existed for millions or billions of years longer than us. Contact with a significantly advanced civilization could be transformative or devastating, depending on their intentions and how the interaction unfolds.
Frank Drake, now in his 90s, remains optimistic despite decades of searching without success. He estimates we may need to search 1 million stars across countless frequency channels before having a good chance of detection. The universe is vast, and technological civilizations might be rare enough that they're separated by enormous distances. Even if thousands of civilizations exist in our galaxy, they might be so far apart that their signals haven't reached us yet, or we haven't looked in the right place at the right time on the right frequency. The search requires patience measured not in years, but potentially in generations. Current searches have examined thousands of stars in detail and millions more in survey mode, but this represents a tiny fraction of the 400 billion stars in our galaxy. If detectable civilizations number in the thousands, we've barely scratched the surface of the search space. Yet Drake insists it's worth it. The eventual discovery, should it come, would be so important that it justifies not just one human life dedicated to searching, but many. It would answer one of humanity's oldest questions: are we alone? The possibility that we might never find aliens, not because they don't exist, but because we lack the capability to detect them, adds another layer of uncertainty. Advanced civilizations might communicate using methods we haven't discovered or can't access. They might use neutrino beams, gravitational wave modulation, quantum entanglement communication, or technologies we haven't even conceived. We're searching primarily in radio and optical wavelengths because that's what we can detect, but aliens might consider those frequencies primitive and obsolete. There's also the zoo hypothesis, which suggests advanced civilizations deliberately avoid contact with primitive ones like us, either to allow natural development or because they find us uninteresting. We might be living in a cosmic nature preserve, observed but not contacted, with aliens waiting for us to reach some threshold of development before revealing themselves. This explanation can't be tested or falsified, making it scientifically frustrating, but it remains logically possible.
Frank Drake, now in his 90s, remains optimistic despite decades of searching without success. He estimates we may need to search 1 million stars across countless frequency channels before having a good chance of detection. The universe is vast, and technological civilizations might be rare enough that they're separated by enormous distances. Even if thousands of civilizations exist in our galaxy, they might be so far apart that their signals haven't reached us yet, or we haven't looked in the right place at the right time on the right frequency. The search requires patience measured not in years, but potentially in generations. Current searches have examined thousands of stars in detail and millions more in survey mode, but this represents a tiny fraction of the 400 billion stars in our galaxy.
If detectable civilizations number in the thousands, we've barely scratched the surface of the search space. Yet Drake insists it's worth it. The eventual discovery, should it come, would be so important that it justifies not just one human life dedicated to searching, but many. It would answer one of humanity's oldest questions: are we alone? The possibility that we might never find aliens, not because they don't exist, but because we lack the capability to detect them, adds another layer of uncertainty. Advanced civilizations might communicate using methods we haven't discovered or can't access. They might use neutrino beams, gravitational wave modulation, quantum entanglement communication, or technologies we haven't even conceived. We're searching primarily in radio and optical wavelengths because that's what we can detect, but aliens might consider those frequencies primitive and obsolete. There's also the zoo hypothesis, which suggests advanced civilizations deliberately avoid contact with primitive ones like us, either to allow natural development or because they find us uninteresting. We might be living in a cosmic nature preserve, observed but not contacted, with aliens waiting for us to reach some threshold of development before revealing themselves. This explanation can't be tested or falsified, making it scientifically frustrating, but it remains logically possible.
Give them water, and tardigrades rehydrate within hours, resuming normal activity as if no time had passed. The dried proteins rehydrate and regain function. DNA uncoils and repairs any accumulated damage. Cells begin producing energy again. Within hours, a desiccated ton transforms back into an active, crawling water bear that feeds, moves, and eventually reproduces. Tardigrades, frozen solid for years, have been revived and successfully reproduced, suggesting that ton state can preserve viability for extremely long periods. Scientists have subjected tardigrades to extreme tests to map the limits of their endurance. Researchers took them to the International Space Station in the European Space Agency's TARDIS experiment, exposing them to the vacuum of space, cosmic radiation, and temperature swings of hundreds of degrees. Space is an incredibly hostile environment with hard vacuum, intense ultraviolet radiation, cosmic rays, and temperature extremes. Yet the tardigrades survived. They were brought back to Earth, rehydrated, and resumed normal life, even successfully reproducing and producing viable offspring. Frozen tardigrades have been shipped from Antarctica, kept at -60 degrees Celsius for years, then thawed and observed under microscopes. When given water, they rehydrated and began moving around as if they'd just been collected from Antarctic moss. This demonstrates extraordinary resilience to both freezing and long-term storage. Some researchers speculate that tardigrades in ton state might survive for centuries or longer if kept frozen or desiccated. These abilities make tardigrades ideal candidates for panspermia, the theory that life can spread between planets or even star systems. If tardigrades can survive space exposure in ton state, could they have hitchhiked to Earth on meteorites billions of years ago? The idea isn't as far-fetched as it sounds. We know that impacts on Mars ejected rocks that eventually fell to Earth as meteorites. Over 60 meteorites of confirmed Martian origin have been found on Earth, blasted off the red planet by asteroid impacts and traveling through space for millions of years before being captured by Earth's gravity.
If similar impacts occurred on planets in other star systems, and if those rocks carried organisms as hardy as tardigrades in Tun state, they could potentially survive the journey and seed life on new worlds. The organisms would need to endure the initial impact shock, accelerating them to escape velocity, survive years or millions of years in the space environment, endure atmospheric entry heating and deceleration, and survive impact with the destination planet. It's a tall order, but tardigrades' resilience suggests it might be possible. When the Israeli lunar lander Bereshit crashed on the moon in April 2019, it was carrying a library of human knowledge and a colony of dehydrated tardigrades in Tun state. The lander was attempting a soft landing, but experienced engine failure and impacted the lunar surface at high velocity, scattering wreckage across the crash site. One scientist, Alejandra Traspas Muina, began to wonder, could the tardigrades have survived the crash? If tardigrades could survive a high-velocity impact on the moon, it would suggest they could also survive crash landings on Earth via meteorites, supporting panspermia. Traspas Muina designed experiments to find out, using a gas gun to fire tardigrades at various speeds into sand, simulating crash impacts under conditions similar to the lunar environment. The gas gun uses compressed gas to accelerate projectiles to hypersonic speeds, allowing researchers to study high-velocity impacts in controlled laboratory settings. At speeds up to 0.7 kilometers per second, about 2,500 kilometers per hour, the tardigrades in Tun state survived. This is remarkable, demonstrating they can endure shocks and accelerations that would pulverize most organisms. But at 0.9 kilometers per second and above, equivalent to over 3,000 kilometers per hour, they didn't make it. The crash forces exceeded even their extraordinary resilience, destroying the Tun structures and killing the tardigrades. The Bereshit lander crashed at higher velocity than tardigrades can survive, suggesting the moon-bound tardigrades probably didn't make it. However, the experiments showed that tardigrades could survive meteorite impacts at speeds typical of some Mars-Earth transfers, which occur at lower velocities than typical asteroid impacts. This keeps alive the possibility that life, or at least hardy organisms like tardigrades, could transfer between planets within a solar system via impact ejection.
Current research investigates whether tardigrades could survive on the icy moons of Jupiter and Saturn, worlds like Europa and Enceladus that have subsurface oceans potentially hospitable to life. Europa's ocean is kept liquid by tidal heating from Jupiter's gravity, despite surface temperatures around -160 Celsius. Enceladus has active water geysers that spray material from its subsurface ocean into space, creating one of Saturn's rings. Could tardigrades colonize the water plumes that erupt from Enceladus, or survive in the ocean beneath the ice shell of Europa? These questions aren't just academic curiosity. Understanding the limits of life's resilience helps us identify where to search for biology beyond Earth. If organisms as hardy as tardigrades exist on other worlds, they might thrive in environments we previously considered lifeless, expanding the definition of habitable zones and potentially making life far more common in the universe than we imagine. The possibility that life on Earth has extraterrestrial origins shifts how we think about our place in the universe. If Earth was seeded by organisms from elsewhere, then life's origin is separated from its current location. We might be descendants of biology that evolved on a completely different world, perhaps in a different star system, carried across the void and deposited here billions of years ago when Earth was young.
In this scenario, Earth isn't where life began, it's just where it currently flourishes. Our entire biosphere could be an extension of life that originated light years away, making every living thing on Earth fundamentally alien in origin. The tree in your yard, the bacteria in your gut, you yourself might all trace ancestry to organisms that evolved on a planet orbiting a star that has long since died. This would mean life is potentially common in the universe, hardy enough to survive transfer between worlds and perhaps even between star systems, seeding biology across the galaxy.
DART targeted Dimorphos, the smaller member of a binary asteroid system orbiting the larger asteroid Didymos. Dimorphos is about 160 meters across, roughly the size of a football stadium. It orbits Didymos every 11.9 hours, locked in a gravitational dance with its larger partner. Neither asteroid poses any threat to Earth, making them perfect test targets. If DART succeeded in measurably changing Dimorphos's orbit around Didymos, it would prove the kinetic impact of technique works. On September 26, 2022, DART impacted Dimorphos at over 6 kilometers per second. The spacecraft, about the size of a vending machine and weighing roughly 570 kilograms, hit the asteroid head-on with tremendous kinetic energy. Telescopes worldwide watched as Dimorphos suddenly brightened, a plume of debris erupting from the impact site and streaming into space. The collision was successful, but had it actually changed the asteroid's orbit? Measurements from Earth-based telescopes revealed that Dimorphos's orbital period around Didymos decreased by 32 minutes, far exceeding the minimum success threshold of 73 seconds. The impact had transferred momentum more efficiently than expected, likely because the ejected debris created additional thrust through rocket effect. Material blasted off the asteroid's surface pushed back against it, amplifying the momentum change beyond what the spacecraft alone could deliver. The European Space Agency's Hera mission, scheduled to arrive at the Didymos system in late 2026, will conduct detailed follow-up observations. Hera will examine the impact crater, measure how Dimorphos's shape and rotation changed, study the asteroid's internal structure, and precisely quantify the momentum transfer efficiency. This data will be crucial for planning future deflection missions if a real threat emerges. But Bennu isn't the only asteroid requiring attention. Over 20,000 near-Earth asteroids have been cataloged, with 1,200 classified as potentially hazardous based on size and orbital proximity. These are objects whose orbits bring them close enough to Earth that a gravitational perturbation from Jupiter or another planet, or a collision with another asteroid, could send them on a collision course with our planet. Tracking these objects and calculating their orbits is an ongoing effort requiring constant vigilance. Asteroid hunters continuously scan the sky, looking for previously unknown objects that might pose threats. Richard Kowalski and astronomers like him spend their nights monitoring telescopes that image the same patches of sky multiple times over several hours. Stars appear stationary in these images, but asteroids move, revealing themselves as points of light that shift position between exposures. Software algorithms automatically detect these moving objects, flagging them for human review. When a new asteroid is found, astronomers track it for weeks or months, gathering enough observations to calculate its orbit with increasing precision. Initial orbits are uncertain, with possible trajectories that might pass close to Earth or miss by millions of kilometers. As
As more observations accumulate, the uncertainty shrinks, and the asteroid's future path becomes clearer. Most turn out to be harmless, their orbits carrying them safely past Earth with no risk of collision. But some require continuous monitoring, their future trajectories uncertain enough that they can't be definitively ruled out as threats. These objects go on watch lists, prioritized for additional observations that will refine orbital knowledge. Occasionally, an asteroid's orbit passes through Earth's position at some future date within the uncertainty ellipse. These objects trigger impact risk assessments, calculating the probability of collision and potential consequences. The process of tracking asteroids and calculating impact probabilities has become remarkably sophisticated. The Sentry Impact Monitoring System at NASA's Jet Propulsion Laboratory continuously scans orbital calculations for all known asteroids, looking for future close approaches to Earth. When potential impacts are identified, Sentry calculates probabilities based on current orbital uncertainties and projects how those probabilities will change as additional observations refine the orbit.
For asteroids like Bennu, decades or centuries of warning time allow for careful planning and multiple deflection options. Even a small velocity change, perhaps a few millimeters per second, accumulates into huge positional changes over years. An asteroid deflected by just 1 centimeter per second decades before impact would miss Earth by hundreds of thousands of kilometers. This is why early detection is crucial. Find the threat early enough, and relatively modest interventions can prevent disaster. The real danger from asteroid impacts extends beyond the collision itself. Pete Schultz's laboratory experiments demonstrate the cascade of destruction these events unleash. Using gas guns to fire projectiles at sand targets at hypersonic velocities, Schultz captures impacts with high-speed cameras running at thousands of frames per second. The footage reveals the sequence of events in exquisite detail. The projectile vaporizes on contact, creating an expanding fireball of superheated plasma hotter than the sun's surface. This plasma engulfs everything nearby, flash heating it to thousands of degrees in milliseconds. Anything within the plasma cloud would be instantly vaporized or incinerated. Shock waves radiate outward at supersonic speeds, compressing and heating the air to create a blast wave that flattens structures and tears apart anything in its path. Winds faster than any hurricane scour the landscape, picking up debris and turning it into high-velocity projectiles. Trees become missiles, buildings are reduced to flying wreckage. The impact would be biblical in scale, a localized apocalypse that would make nuclear weapons look quaint by comparison. And this is just from laboratory simulations of small impactors. Scale up to asteroidal sizes, and the devastation becomes planetary.
Beyond DART's kinetic impact technique, scientists have proposed other asteroid deflection methods, ranging from practical to outlandish. Nuclear explosions detonated near but not on an asteroid could vaporize surface material, creating thrust that pushes the asteroid off course. This method avoids the problem of radioactive fragmentation that would occur if the nuclear device actually contacted the asteroid. Instead, the explosion's X-rays and neutrons heat and vaporize surface material, creating a rocket-like plume that propels the asteroid. Calculations suggest a single megaton-class nuclear device could deflect a 200-meter asteroid by enough to prevent impact if deployed decades in advance. The advantage is that nuclear explosives deliver enormous energy in compact packages, making them feasible for launching with current rocket technology. The disadvantage is political and practical. No nation wants to normalize placing nuclear weapons in space, and ensuring the device detonates at the optimal position and time presents technical challenges.
gravity tractors would fly alongside asteroids for years or decades, using their tiny gravitational pull to gradually alter the asteroid's trajectory. A spacecraft weighing several tons hovering near an asteroid would exert gravitational attraction measured in micronewtons, absurdly small compared to everyday forces. But applied constantly over years, this tiny tug accumulates into measurable velocity changes. The advantage is precise control, with no risk of fragmenting the asteroid. The disadvantage is extremely long mission durations and the requirement for highly stable, long-lived spacecraft. One particularly creative proposal involves paintballs loaded with reflective powder. Shooting an asteroid with millions of paintballs would serve two purposes. First, the impacts themselves impart momentum, contributing a small immediate velocity change. Second, coating the asteroid with white reflective paint increases solar radiation pressure, the force exerted by sunlight hitting the asteroid's surface.
Sunlight carries momentum, and when photons reflect off a surface, they transfer momentum just like bouncing balls. For a dark asteroid, most sunlight is absorbed, transferring minimal momentum. Coated with reflective white paint, and suddenly photons are reflecting efficiently, doubling the momentum transfer. Over years or decades, this solar photon pressure could push the asteroid measurably off course. The downside is that this method needs about 20 years to achieve significant deflection, requiring very long warning times and early intervention. Some proposals involve attaching solar sails or ion engines directly to asteroids, turning them into slow but controllable spacecraft. An ion engine mounted on an asteroid could fire continuously for years, gradually changing its velocity through sustained low thrust. Solar sails would deploy large reflective surfaces that use solar pressure for propulsion. Both methods offer high precision and control, but face challenges with asteroid attachment and operation in the harsh space environment. The philosophical question underlying planetary defense is whether we have a responsibility to protect Earth from asteroid impacts when we have the capability to do so. The dinosaurs couldn't prevent their extinction, but we potentially can. We possess the technology and knowledge to detect threats decades or centuries in advance, and the capability to deflect them before impact. Failing to develop and deploy planetary defense systems when we have the resources to do so would be a form of negligence, allowing a preventable catastrophe that could kill millions or billions. On the other hand, the resources devoted to tracking and deflecting asteroids come at opportunity costs. Money spent on telescopes, spacecraft, and planetary defense infrastructure could fund other priorities like climate change mitigation, pandemic preparedness, poverty reduction, or basic scientific research. The probability of a civilization-ending asteroid impact in any given year is low, perhaps 1 in a million or less for the largest impacts. Do we focus resources on near-term threats like climate change and nuclear war, or prepare for rare but catastrophic events like asteroid impacts?
Most planetary scientists argue we should do both. The cost of comprehensive asteroid detection and deflection capability is modest compared to global GDP, perhaps tens of billions of dollars spread over decades. This is affordable insurance against an existential threat. Moreover, the technologies developed for planetary defense have other applications. Advanced propulsion systems designed for deflection missions could enable deep space exploration. Improved tracking systems help with space situational awareness and debris monitoring.
universe whispers its secrets to those patient enough to listen, speaking in languages of mathematics and light, gravity and time. These sleepy facts about the cosmos accumulate into an overwhelming picture of reality far stranger than everyday experience suggests. Space is expanding and accelerating, driven by mysterious energy we cannot explain. Time flows at different rates depending on gravity and velocity, with clocks running slower near massive objects. Particles exist in multiple states simultaneously until observed, their quantum superpositions collapsing into definite outcomes when measured. Matter comes in forms we cannot detect, dark matter holding galaxies together through gravity alone while remaining invisible to all electromagnetic radiation. Energy manifests in ways that defy explanation, dark energy accelerating cosmic expansion in apparent violation of energy conservation. The universe might be one of infinitely many in a vast multiverse, each with potentially different physical laws and histories. Life might be common or impossibly rare, with Earth hosting the only biology in the galaxy or even the universe. Or perhaps life thrives on countless worlds, with intelligence arising wherever conditions permit and technological civilizations scattered across the cosmos. We might be alone, or surrounded by intelligence we cannot recognize because it operates on principles we haven't discovered.
These mysteries don't diminish as our knowledge grows. They deepen. Each discovery reveals more complexity, more questions, more unknowns lurking just beyond current understanding. The universe seems designed to remain perpetually mysterious, offering just enough clarity to keep us searching while withholding final answers that may never come. Perhaps that's the point. Perhaps consciousness exists not to know everything, but to wonder at existence, to grapple with mystery, to find meaning in the search itself rather than in final answers. As dark energy continues accelerating the universe's expansion and you drift towards sleep, remember that you're part of this cosmic story. Your consciousness, brief as it is on cosmic timescales, represents the universe becoming aware of itself. You exist during a window of cosmic time when complexity is possible, when stars shine and planets orbit and life emerges and evolves into beings capable of contemplating existence. This moment is fleeting. In the deep future, trillions of years hence, the universe will become cold, dark, empty. Stars will exhaust their fuel and fade. Galaxies will drift beyond each other's cosmic horizons. Black holes will evaporate into nothing through Hawking radiation. The cosmos will approach maximum entropy, a state where nothing interesting can ever happen again, where the arrow of time loses meaning because no change is possible. But that's incomprehensibly far in the future. Right now, the universe is alive with possibility. Stars are being born in nebulae, planets are forming in protoplanetary disks, black holes are colliding and merging, neutron stars are creating heavy elements, and somewhere, perhaps on countless worlds, life is taking its first tentative steps from chemistry into biology, from simple replicators into complex ecosystems, from unconscious matter into minds that can wonder why anything exists at all. And perhaps that itself is the deepest mystery. Not the nature of dark energy or dark matter, not whether parallel universes exist or whether we're alone in the cosmos, but why there is something rather than nothing. Why does the universe exist? Why are there laws of physics rather than lawless chaos? Why is the universe comprehensible to minds like ours? Why does mathematics describe physical reality with such uncanny precision? These questions may have no answers, or the answers may lie forever beyond human comprehension. But asking them, grappling with them, feeling the weight of cosmic mystery pressing down on our brief flicker of awareness, this is what it means to be human. To stand beneath the night sky and feel simultaneously insignificant and profound, tiny and vast, ephemeral and eternal. You are made of star stuff, atoms forged in stellar furnaces billions of years ago, cycled through multiple generations of stars before eventually assembling into your body. You're not separate from the cosmos. You're a temporary arrangement of matter that came from stars and will return to space when your pattern dissolves. For a brief moment, these atoms gained the ability to contemplate their own origin, to wonder about their place in existence, to search for meaning in the vastness. And as you close your eyes and consciousness fades into sleep, these cosmic mysteries continue unfolding. Dark energy pushes galaxies apart. Neutron stars spin hundreds of times per second. Black holes devour matter and warp spacetime. Fast radio bursts flash across the universe, and somewhere, in some corner of the cosmos, another being might be looking up at their sky, wondering the same questions, feeling the same cosmic loneliness and wonder, searching for answers that may never come.
The universe is vast and strange and beautiful and terrible, full of wonders we're only beginning to glimpse and horrors we can barely imagine. It doesn't care about us, doesn't notice our existence, will continue its expansion and evolution long after humanity is dust. Yet here we are, briefly aware, asking questions, seeking understanding, trying to make sense of it all before we too return to the cosmic dance of matter and energy from which we briefly emerged. Sleep well, knowing that you're part of something infinitely larger than yourself, connected through space and time to everything that has ever existed or ever will exist. The atoms in your body have witnessed the birth and death of stars, have drifted through interstellar voids, have been part of asteroids and planets, and perhaps other living beings across billions of years. Now they're you, and tomorrow they'll be something else, forever recycling through the great cosmic cycle that has no beginning and may have no end. And perhaps, just perhaps, in some parallel universe, another version of you is reading these same words, making different choices, living a different life, but asking the same eternal questions. And perhaps, in bubble universes beyond our cosmic horizon, beings we can never meet are discovering their own mysteries, unraveling their own cosmic secrets, adding their own brief spark of consciousness to the vast and ancient darkness. The void between stars is not empty. It's full of possibility, pregnant with mystery, alive with questions waiting to be asked, and perhaps never answered. And that's exactly as it should be.